And it's a nice simple way to take attendance and to give you credit for coming on a snowy sort of morning. So it will ask you for the magic word for today. And you simply enter the word snow. Okay? And that's 10 points on your score. You can tell other people about this if you want, but I wouldn't. So, all right, today we're going to do, it's kind of a fun lecture, a little bit of earth science, if you will, and we'll try to get some chemistry in there too. We're going to talk about some earth chemistry. Now, we're all familiar with the earth, that's where we live, this big blue ball. What we see up here is really just the crust, the very top of the crust. This is continental crust. Underneath the oceans, we have a much denser crust, the oceanic crust.
How you doing?
Ah. Side doors open?
No, we're just bringing chairs back.
Oh, okay.
Just double check.
Yeah, it worked this morning. But the really interesting stuff is deep inside. This is the series of pores and mantles and things like that that are associated with the interior of our Earth. Down here at the very center, we have the interior core. It's a solid ball. It's made mostly of iron and nickel. And it's only about 800 miles across, so it's a little tiny thing. Its temperature is about 5,400 degrees centigrade, which is well above the melting point. But because it's at the very center of the Earth, you have great gravitational forces pushing on it, and that's enough to keep it a solid ball. Very hot, though. The next layer out is referred to as the outer core. Again, this is about 4,000 or so degrees, so it's really hot. And this one is molten. It's the same mixture as in the inner core. It's an iron-nickel mixture, and it's about 1,400 miles thick or so. On top of that, we get fluid layers, referred to as the various mantles. The mantle close down to the outer core is about 4,000 degrees, and as you get closer to the surface here, it drops to about 500 degrees. It is still fluid though. And because it's fluid, it can undergo convection. Now, when this undergoes convection, what this basically means is that the hot molten rock that makes up the upper layer of the mantle is going to be rising. Imagine you're cooking pasta, okay? And you have the pot boiling. The pasta just kind of rolls around in the pot. That's the same sort of phenomenon. Our two layers of crust here on top of the mantle are the continental. The continental crust is thick, relatively buoyant, if you will, lower density. And the oceanic crust underneath the water is compressed by the weight of the water. It's much, much denser and a narrower sort of layer. When the mantle heats up, like it does, it causes these convections. So this is a thermogram showing convections. We've heated up the bottom here. Things tend to rise. When they hit a layer up here, they spread open. Well, this is what it looks like inside the Earth. We have the top layer of the mantle, and it's heated up a lot. It convects up, and it spreads out. Now, this is molten rock, mind you. So this happens very, very slowly. It's a very slow but steady convection. Now, when this happens, it tends to cause breaks in the crust. So this represents our top continental crust, if you will. This is the top layer of the mantle, and this is where we have all these convections happening. As this stuff bubbles up, it will tend to cause a weakness and actually break the crust open. As it does, it pushes it to both sides, replaces it with mantle rock, and this slowly moves in both directions. Now that means now it has to go somewhere. So what happens is we get other weak spots in the crust. This slab will tend to be pushed down underneath, forming a trench, but this basically recycles this whole section over and over and over again. A very slow sort of phenomenon. Here's another image, and you can see we have an uplifting here, and this tends to form a ridge. Over here, for example, we have this bit of crust going this way, pushing this one down as it goes around. Same sort of thing will happen over here. This is what's referred to as the concept of plate tectonics. The entire crust consists of a series of plates. Now, these are all the plates that are known, and there's a whole lot of them. Just to make it a little bit simpler, I've colored in North America here, so we can see this is all part of one plate. Here's a little Caribbean plate. It's a separate thing. This is out over the Pacific Ocean. Down here, we have South America. Another plate next to it, one on this side. Over here is Africa. And up here is the Eurasian plate. So there are lots and lots of plates. These are just weaknesses of the crust that are undergoing this recycling thing as these things, the hot mantle swells up. Where it comes up and breaks into the crust, this is called a divergent boundary. So we're actually spreading the crust on both sides here. Again, this is continental crust. This is the much denser oceanic crust, and it will just tend to run down underneath the continental crust on both sides. So kind of just swirling around like that. Now there are two important things. One is, we'll talk about the boundary thing here, what happens at this point, and what happens out here where the oceanic slides underneath the continental. When it slides underneath the continental crust, so this is the oceanic crust, it's nice and dense. This is the buoyant or less dense continental crust, and this is being pushed down underneath. As it does, it generates a huge amount of heat. Enough heat to melt this series of rocks right here at the boundary. And what that does is tend to form a line of volcanoes. So this is where lava comes from. This is heat generated by this crust going one underneath the other. This is called subduction, when one goes underneath the other. It generates heat, and we get volcanoes. If you look up in the northwest of the United States, this is what's going on. We have an oceanic crust going underneath the North American plate, and you've heard of Mount St. Helens and all of those guys. These are all part of the Cascade mountain range, and this is just lava from where these two plates are interacting with each other. South America, it's even more obvious. We have a huge plate out here that's subducting underneath this continent, and when it does, it's generating the Andes, this huge mountain range that's very, very active volcanically. When this happens in the middle of the ocean, now it doesn't always have to happen at a continental mass, we can have one slab of oceanic crust going underneath another. When this does, the volcanoes that form here tend to burp up, and we wind up with chains of islands. This is where Hawaii came from. Most strikingly, this is where Japan came from. This is the entire Japanese island system, and all of these little red spots here, I'll enhance that in a second. All these little red spots are volcanoes. So as these plates slide underneath each other, the two oceanic plates, we generate all of the islands of Japan and this huge volcanic activity. The Aleutian Islands, up there by Alaska. This is one plate, again, sliding underneath another, and all of these guys are active volcanoes along this thing. So that's where this all comes from. Probably the most striking thing when these plates hit each other is when they hit each other as two continental crusts. When two continental crusts collide, what they do is they don't generate volcanoes, but they tend to just push this crust material up higher and higher, and that makes the big, ugly mountain ranges. The Alps and the Himalayas are examples of where this has happened. And again, these are very impressive mountain ranges. This is the Alps, very pretty. These are the Himalayas, not quite so pretty, but certainly very, very stark mountains. Now, when all of this crust is moving around, it occurred to people, in the 70s or so, that, gee, this is going to do something to these continental land masses as well. And this is the concept of continental drift. If you've ever looked at a map and looked at the shape of South America and Africa, they kind of like fit together, don't they? There's got a big bump here and a big hole here. That's because they used to be together, actually. And they broke apart along this plate. A long, long time ago, a galaxy far, far away, all of the continental land masses were all connected. Everything else was ocean. And this supercontinent is what is called Pangaea. Pangaea, because of the action of these, the mantle swelling up and the divergent boundaries and stuff like that, broke into a series of plates. These plates moved apart and gave us the continents that we see today. Kind of a very interesting process. This is a rendering, a computer rendering, of the ancient Pangaea. Again, it's one massive continent. And you see you've got lots of little plate boundaries in here. You can kind of pick out many of the continents. Over time, this is what happened. You see the continental plates start to divide up. They start to break. Here goes North America. There's Florida. This little lump here winds up as the Yucatan. Finally, Africa, South America break apart. We have Antarctica down here, Australia. And these guys work their way up and eventually touch. The most striking thing here to me, as I watch this, and let's watch it again, is India. Let's watch this thing again. Now, India starts off down here, connected to Antarctica and Australia. They break apart. Finally, they break apart. Here's Antarctica, here's Australia. Now watch what India does. Really gets going here and slams into the underbelly of Asia. And that's where the Himalayas came from. India just slamming in to that other continental shelf. Now, almost everything that we have on the continental crust is our basic, the stuff that we see every day, the rocks, the granites, and stuff like that. There are a few places on Earth where mantle is actually exposed. Not too many, and that's a good thing, because the mantle, unlike the continental crust, is very, very rich in heavy metals. When we say heavy metals, we're talking about old things like lead, mercury, actually gold and silver and stuff like that are in there. But these are very, very toxic. They're toxic to people that live here on the surface. So these are large sections of land that are basically uninhabitable because we've got just huge concentrations of heavy metals. The continental crust, however, is much more civilized. Lots of oxygen and magnesium, lots of silicon. Silicon's very, very common. And it goes down here. By the time you get to potassium, you've already accounted for over 99% of the stuff. Did you have a question?
Yeah, quick question. Now, we have saw like India move like the most. Do they know why it moved the most?
Yeah, why it moved the most, it was just a very active plate. Just a very active plate. Lots of upwelling. It must have been a really weak section in the crust there, so that the mantle could really pull up quickly and just slam this sucker up there. It's an amazing animation to watch. It really is. Over here on the compounds that we get, silicon dioxide, that's sand, and 46% of what we have here in the continental crust is basically sand. A lot of magnesium, some iron oxide, aluminum, calcium salts, lots and lots of oxygen, as you can see. Oxygen is a very, very common element in the crust. This gets down to 99.1 by the time we get to potassium oxides. Now, the crust that we have is very rich in minerals. We refer to those minerals generally as ores. This is an example of what's called a banded iron ore. The little stripes that you see through here, this is iron 3 oxide. Iron 3 oxide is what we use when we refine the ore and convert it into metallic iron. There's also a lot of manganese. This is a nice lump of manganese ore. Manganese ore tends to be very, very rich in the metal, very easy to extract. In fact, at the bottom of the deep oceans, there are just huge lumps of nodules that are referred to of pure manganese metal. Difficult to get all the way down there to mine them, pick them up, but there's a whole lot there. The process of refining an iron ore follows a very simple equation, something like this. And this is the process that goes on at the big plants like in Gary. You take the iron 3 oxide and you take carbon monoxide. Now, carbon monoxide is produced from coke. Coke is coal, basically. You heat it up, you make carbon monoxide, you get what's called a single replacement reaction. The result of that is to form metallic iron and CO2. Metallic iron, of course, is what we're after. Now, this reaction is something that you really can't do in the lab for a demonstration or whatever, but there's a very similar single replacement reaction. Instead of using carbon monoxide, what you use is aluminum metal. This is what's called the thermite reaction. You just stuck a piece of magnesium that was burning. You did that in the lab. This is a little flower pot. And a little flower pot, of course, has a hole in the bottom. As this reaction goes, it This is metallic iron. The metallic iron dribbles down through this hole into this big flower pot. So aluminum plus iron 3 oxide gives metallic iron and aluminum oxide. Very, very nice, fun reaction to do in lab. We can't quite do that in the classrooms like we used to in the old days. That was so much fun. But when you're done, here he's picked up the lump of iron that fell down. And you see it's a very, very intense, very hot chunk. When it finally cools, you can clearly see that it is, in fact, this really nice chunk of iron metal. The bad thing about thermite, you saw that little fire as it went. This is what they used in incendiary bombs in World War II. They would fly over cities and drop this stuff and land, rooftops everywhere else, and do this thermite reaction, and it was just really terrible stuff. Bad stuff, don't do that. But it's a really fun reaction to do. Take a close look at this equation for the thermite reaction. Make sure you know it, because you might see it again. I'll pause for a second. That was a hint. Now we said that the Earth's crust contained lots and lots of silicon, mostly as silicon dioxide, that's sand. The most common form of coordinated silicon, however, is what's called silicates. Silicate anion has a -4 charge, has 4 things around the silicon, so it's tetrahedral, and it tends to form minerals. Lots and lots of really interesting minerals with lots of interesting metals. This is zirconium silicate, also called zircon, and you can see it is crystalline, not real pretty. Here we've stuck in manganese and aluminum with a silicate, and we can make very fine gemstones out of these. This is not cubic zirconia. Cubic zirconia is actually zirconium dioxide, ZrO2, and it can be cut. It's very similar in makeup to diamonds. Actually, the latest advance in all of this uses something called silicon carbide, SiC, that forms a crystal structure, can be made in the lab, and is very, very, very similar to diamonds. Really hard to tell them apart. This stuff, we stick in some uranium. Potassium uranium is hydrated. Beautiful crystals. Here we have calcium and chromium as a silicate. Again, very nice crystals. These guys make gemstones. Now, if you take silicon dioxide, which we said was the most common form of silicon on the crust, if you have pure silicon dioxide and it has crystallized into these beautiful little thingies, this is what we call quartz. Quartz, in quartz, the silicon dioxide is arranged in little tetrahedra, with the silicon actually being shared by 4 oxygens. But it's an extremely regular structure. This extremely regular structure is what gives quartz crystals their really unique and very beautiful shapes. If you take silicon dioxide, basically the quartz structure, and instead of having this 3-dimensional array, if you make it with a 2-dimensional array, so each of these represents a silicon bonded to the 4 oxygens, you get what's called mica. Same thing, silicon dioxide, but it's just 2-dimensional. Mica forms as these little thin sheets. It's very heat resistant. Back in the old days, if you had an oven or a stove or something, and you needed to be able to look in to see it, what they used was thin sheets of mica that you could see through. but they were very heat resistant because they're just silicon dioxide. If you take this and arrange it as a one-dimensional array, we get asbestos. So these are asbestos fibers, little wee tiny things. Now for many, many, many years, asbestos was used for insulation. That's because you could take these fibers, kind of blow it open, and you get lots and lots of dead air space in between. That meant that it was very, very slow to conduct heat. So asbestos went in absolutely everything. It was, a great thing. They made shingles out of it and put them on people's houses, etc. Wrapped all the pipes in asbestos, whatever. Problem with asbestos turns out, though, that these little tiny fibers, they're microscopic. They're like little tiny needles. And if you happen to inhale asbestos dust, what happens is it goes into your lungs, and these little needles tend to just pierce themselves into cells. This causes great irritation, of course, in the lung, and eventually will wind up with a very specialized type of cancer called mesothelioma, where you have damage to the mesothelium by the asbestos, and that eventually leads to a cancer. If we take silicon dioxide and totally destroy the irregularity here, you get what we refer to as glass. Glass is basically just silicon dioxide in an absolutely random array. Now, because this is totally random, there is no crystal structure. That means that glass is actually a fluid. Glass will flow. Now, that's how we mold glass into things. You can take it, heat it up. Once it's nice and warm, it flows. Blow it into different shapes and stuff like that. But even after it cools, it's still an amorphous solid. And it will, over time, just flow all by itself, just through gravity, whatever. Kind of an interesting sort of stuff. So depending upon the crystal array, silicon dioxide could go all the way from quartz through mica, asbestos, and then amorphous, we wind up as glass. Cement. Within the Earth's crust, there's a lot of calcium. And the calcium tends to combine with carbon dioxide, and it makes calcium carbonate. This is limestone. Big buildings are made of limestone. Chalk is basically pure calcium carbonate. If you take calcium carbonate, this was discovered back in Roman times. If you take calcium carbonate, you can heat it up. When you heat it up, calcium carbonate decomposes, and it forms calcium oxide and CO2. Now, calcium oxide is the stuff we call lime. It's irritating. But the neat thing about it, what the Romans discovered, was that if you took lime, mixed it up with water, you get this slurry, this ugly slurry, and then allow it to sit, it will absorb CO2 from the atmosphere. And when it does, it reforms calcium carbonate. So calcium carbonate, we just said, is effectively limestone, isn't it? This is the very basics of cement technology. Start off with calcium carbonate, make lime, mix it with water, let CO2 recombine, and by gosh, you've got a rock again. Now today we don't do it quite this way. Today they use what's called Portland cement. Romans did too, sort of, as they developed more technology. What you do is when you heat your calcium carbonate, you make sure you have some sand in it. calcium or silicon dioxide. When you do this, you get a silicated lime. And the silicated lime, once it absorbs, makes the cement that we see today. This is called hydraulic cement. But hydraulic cement is much, much, much stronger than the original cement, just made from calcium carbonate. All right, let's leave the crust and let's head up to the top of the Earth, the outer layer. This is the atmosphere. Atmosphere, of course, is very important because we have to breathe. It also absorbs energy from the sun, warms things up. It recycles water, so water goes up, clouds, comes down again. It protects us from high energy radiation. We'll talk about that. And of course, it protects and supports life. We need oxygen to breathe. So we're dealing with the outer fringe here now of our little blue ball. The atmosphere is actually just a mixture. It's a homogeneous mixture of gases. It's mostly nitrogen, about 80%, got about 20% or so oxygen, and then trace amounts of other things. The other things, we have argon, carbon dioxide, and other gases. So mostly it's just nitrogen and oxygen. Now this tends to layer itself over the crust, and we form 4 layers that have been identified, at least 4. Troposphere is down here at the bottom. That's where we live. Up here we have stratosphere. That's where planes fly. This is where ozone lives. We'll talk about ozone in a minute. Mesosphere, we're getting way up here. This is like where the shuttle would orbit. And then way up top, we have what's called the thermosphere on the very top. The troposphere, again, this is where we live. It's about 16 kilometers, so that's 8 miles or so thick down here. This has most of the mass. Again, it's held in by gravity. The troposphere, the temperature decreases with altitude about 6 degrees centigrade per kilometer. By the time you get to the top here, it's minus 50. So it's very, very cold at the top of the troposphere. The stratosphere is probably the most interesting. It extends from about 10 to 50 kilometers. This is the thing here. This is where planes fly. It's less dense. It has very little water vapor in it. The interesting thing about the stratosphere is that the temperature dependence is inverted. As you go higher in the stratosphere, the temperature actually increases. Now, the reason that it increases has to do with the gases that are up here. As you get to the top, they absorb lots of energy from the sun. Remember, the faster a gas particle moves, the higher its kinetic energy, and that's related directly to its temperature. So up here, it's, quote, higher temperature. However, if you were standing here, aside from being dead, you would not feel like it was warm at all. It would be about minus 50 degrees centigrade. But that's because the air is so thin. The gas particles are still traveling very, very fast, but there aren't enough to hit you and warm you up. Mesosphere. Again, we're back to the point, because there's so little gas up here, temperature, again, decreases. And the most amazing to me is the thermosphere up here. This is way up in space where we have satellites. there's very, very, very little gas up there. But what gas is there really absorbs sunlight like mad, and it can be 1,500 degrees. But again, you would freeze to death instantly because there's not enough gas to keep you warm. But the gas that's there is really hot. Now, in Paris now, people are talking about greenhouse gases. Let's talk a little bit about the greenhouse effect, how it comes about, and we're going to revisit this in just a little bit when we talk about climate change. We have light coming in from the sun through this layer of atmosphere, these 4 layers we just talked about. As the visible light works its way down, it hits the earth and the oceans and stuff like that, and it warms them. Now, when something is warm, it emits radiation. This is infrared radiation. Infrared radiation radiates off of the earth and back up into the atmosphere. If we have what are referred to as greenhouse gases in that atmosphere, some of this radiation is absorbed by the gases. They get all excited and they radiate that in all directions. So what that means is that as this radiation, instead of just escaping, as this radiation hits these gases, this radiation is reflected back towards the earth. And so we wind up with an increase in temperature due to these gases. Greenhouse gases, water vapor, well, there's not much we can do about that one because the earth is totally covered with water. That's a good thing. CO2, ozone, and methane. The 2 that we're really concerned about these days are carbon dioxide and methane. Both of these are very effective greenhouse gases. So they absorb this infrared radiation and then radiate it back towards the earth. I guess once this radiates back, it causes the lower atmosphere here, the troposphere, to warm, and that would give us warming. Now, in terms of greenhouse gases, not much you can do about water vapor or ozone, but been a 15% increase in the concentration of carbon dioxide in the last 100 years. Now, this comes because we've gone from agricultural to industrial, so we're burning coal, making energy, stuff like that. We have cars, factories, and all of these things produce CO2. The effects, well, we're going to have this radiation coming back at us, and that's the phenomenon called global warming. Global warming can affect the polar ice caps. We're going to raise the temperature of the troposphere that melts the ice, also warms the oceans. Warming the oceans. Remember when you have a tropical storm or hurricane form, the thing that drives that is convection currents off of the warm ocean. So the warmer it gets, the more powerful the storms are. Yeah?
That was a good question. Now, you said that it hits like the gases or something? Like now, does all of it come back to the earth?
No,
Some of it.
it's radiated out in all directions.
Okay.
But some of it
Okay.
is, the part that's pointing down in my diagram. That stuff comes back. So instead of escaping, like it would if it was nice, we get this stuff coming back. The higher the concentration of greenhouse gases, the more it's reflected back towards us. We also said that in the stratosphere, we had an ozone layer. Now, ozone is a greenhouse gas, but it's way up in the stratosphere, and it forms another function that's actually really, really useful, really important. Turns out that ozone is very good at absorbing ultraviolet light. The sun puts out lots of ultraviolet light. Ozone absorbs it, and when it does, it cuts the amount of light coming down so that we're not bombarded by this ultraviolet radiation. Now, back in the old days, chlorofluorocarbons were used in refrigeration. We'll talk about this in a second, but this is an example of Freon. Freon, it turns out, will catalyze the breakdown of the ozone layer. When the ozone layer breaks down, ozone is replaced with oxygen. Oxygen does not absorb the UV light, and this stuff just comes pouring straight on down. We'll talk about the chemistry involved in this in just a minute, but the ozone layer is very important in terms of protection. We've all heard of UV light being broken down into UVA and B. Okay, when we buy sunscreen, that's what we're after, is UVA and B. Turns out that ozone, very effective at absorbing UVB. UVB is the highest energy. If you get UVB radiation, it causes damage to your skin, damage to your DNA. It's really bad stuff. Ozone protects us from that. So we'll talk a little bit about the chemistry of that in just a minute. I said that the chlorofluorocarbons were catalyzing the decomposition of ozone. Nobody ever expected this to happen. In the 70s, technology finally got to the point where you could put satellites in orbit. And they had sensors on them, and you could measure things. And one of the things that people measured was the concentration of ozone in the stratosphere around the world. To everyone's surprise, the map looks something like this. Green is good, lots of ozone. But over Antarctica, and actually over the Arctic as well, there was a hole in the ozone layer. Now, why does this happen at the poles? Because the poles are so very cold that there's a huge circulation of atmosphere around them. So it tends to circulate just like the eye of a hurricane. And it will concentrate these gases in the regions here over the poles. Well, when scientists discovered that there was a hole, they very quickly figured out that it was the chlorofluorocarbons that was doing it, and they were banned. Now that's a good thing. Everybody says we can't do Freon anymore. That's why when you go get your air conditioner fixed now, it's really expensive. Freon was cheap. It's really expensive because you have to use things that don't hit the ozone. The chemistry involved in the breakdown is free radical chemistry. Now, we've dealt with carbon with a valence of 4. But you can form carbon radicals. A radical is simply something that has one unpaired electron. This is methane. If a radical interacts with methane, what it will do is simply pull off a hydrogen atom. When it does, it converts this into a carbon radical. Now the carbon radical here is trigonal. The radical itself lives in this p orbital. And this is called a calculated spin density. Again, it looks a lot like a p orbital. And this is where the radical actually exists. you can form radicals thermally, or you can form radicals from high energy light. And that's what was happening with Freon. This is Freon 11, trichlorofluoromethane. Turns out that if you take Freon 11 up into the stratosphere, that it can interact with sunlight. The sunlight will split off one of these chlorines to form a chlorine radical. All right, now up in the stratosphere we said there was also ozone. This carbon radical can react with ozone. Ozone is O3, and when it does, it forms this hypochlorite radical and oxygen. So this is the reaction where ozone goes to oxygen. A good thing to absorb UVB, doesn't absorb at all. Now the hypochlorite radicals can combine to form this peroxy radical. This can then split off a chlorine radical on the end and do this sort of chemistry. Now, this is a little complicated, I suppose. I'm never going to ask you to write these equations, but what I want you to realize here is what we have done is we have started this cascade with a chlorine radical, haven't we? And here in our very last step, we've made a chlorine radical. This means that this is a chain reaction because this radical that goes back and does everything all over again. Does this and cycles over and over and over and over. So theoretically, one molecule of Freon here can destroy thousands of ozones. This is the chemistry behind depletion of the ozone layer. Now this is what the initial imaging looked like in '79. This is Antarctica here, and this is our hole. By the mid-90s, we had a really striking hole. Got a little better in '97, worse here, little better, a little worse. 2002 really looked promising. Remember, the use of Freon, etc., had been banned already. So the thinking was, we're actually winning, that we're going to be able to restore the ozone layer. However, fast forward to 2012, this is the largest ozone hole that's ever been observed. If you take this and do a density map, this is Antarctica here, the height and the color represents ozone concentration. And you can see down here, right around Antarctica, it's just a giant hole. It's just totally missing. Now, one of the compelling arguments that people made in order to get people to ban Freon was they calculated globally what was going to happen if we did. This is the animation for that. This starts in the mid-70s. This is North America, so well, this is where we live, that's good. And you see we have a fairly nice ozone protection layer over us. Down here towards the equator we have less, but it's certainly not a hole like we have down in Antarctica. What they did is they calculated what was going to happen to the ozone layer over time if we did not ban Freon. The images look something like this. At 74, by 94, it's starting to get less. 2009, the blue keeps creeping up. 2040, the tropics, you don't want to go there. And by 2060, essentially all the ozone would have been gone. Very, very striking calculations. Again, down here in the tropics, the sun just would have eaten through you, and frankly, everywhere by the middle of the century. So we've made progress, but still, for some reason, we're having trouble controlling the ozone layer. Again, there's a fairly decent hole in the Arctic now, as well as a nice big one in the Antarctic. Any questions? All right, let's return to greenhouse gases. And let's look at the concept of global warming. We're going to focus here on carbon dioxide. But carbon dioxide really isn't the only bad player. Methane is also very, very prominent as a greenhouse gas. Methane, of course, comes from decomposing garbage and stuff like that. But the real source of methane that everybody is or should be worried about is the permafrost. Permafrost, permanently frozen ground. So you're talking about at the poles. That's a huge, huge concentration of methane frozen inside this ground. If this stuff thaws, all of this methane is going to be released. Go up in the stratosphere, and we're going to really, really warm, and very quickly. In 71 to 2005, CO2 vehicle emissions rose 18 billion tons per year, up to 4.6 billion tons. Now the global temperature increased about half a degree century, or half a degree centigrade during the last century. Most people predict that if things continue, that at least by 2000, or 2100, we're gonna have an average 2-degree warming. Sea level has risen, and when the polar ice caps melt, it could really, really rise 25 feet or so. This is CO2 emissions, or total global. This is mostly greenhouse due to CO2. And again, you can see from 70 to 2004, it's just going up steadily. There seems to definitely be a correlation between CO2 and temperature. Here we have them both plotted. The red line here is carbon dioxide, and the ragged blue line from the mid-1800s all the way to 2000 or so represents average global temperature. The two correlate very nicely, and they go up. Now, what I want you to appreciate here is how much it's gone up. Say we're starting off here about minus 0.5. Really, we've gone up a degree, less than a degree centigrade. You might argue, gee, that's really not much. That's really nothing to worry about. Ever heard of the Little Ice Age? Think way back in history. Your history class. Everyone took one sometime. In medieval times, things were nice and toasty. This is about the year 1000. It was a nice, toasty, warm environment, relatively speaking. This is called the medieval warm period. Nice and happy here. For some reason, nobody quite knows why, but for some reason, the temperature started dropping. And by the time you got to 1700 or so, we had dropped essentially 0.8 degrees. 0.8 degrees centigrade, that's all. This set off what was called the Little Ice Age. In the Little Ice Age, the canals in Venice froze solid. All the rivers in Europe froze solid. It was just an extremely cold time. This is an image, a painting from the day. This is the Thames River in London. This London Bridge goes across it. Big river. It froze so solid that they used it kind of like as a park. This is an image, this is called the Frost Fair. So they set up tents and whatever and just had a big good time here on this frozen river. It's frozen again for long, long periods of time. And all of this was just less than 1 degree centigrade. Now we're doing the opposite here. We're on the opposite end. Our greenhouse gases are going up. As they go up, we're warming. Now we've already said that warm water is going to tend to breed giant storms. We've already had several absolutely remarkable hurricanes or typhoons in the Pacific. We've had a couple of Atlantic storms that are just about as big. We're also having melting of the polar ice caps. And like I said, this is a very nice animation or a very nice Photoshop job. But if we raise our sea levels, if we let the ice caps melt and the sea level rises, all of our coastal cities, like New York, are going to be totally underwater. Most of the islands of the Caribbean will be gone. Most of Florida will be gone. So it's a very, very potentially bad problem. It's also just, in fact, going to get really warmer. As it gets warmer, you're going to have trouble growing crops and stuff like that. That's bad. This is projection of, say, 2070 to 2100. Average temperature increase. So this is a lot here over South America. You see how much the poles would have warmed. So this is a differential. Chicago's right here, isn't it? We're in the middle of this fairly warm spot. They're predicting about a 6 degree increase in temperature, average temperature in Chicago area. 6 degrees, well, that's about 10 degrees Fahrenheit. So on a really hot day in Chicago, we can hit close to 100. You know, that's danger, right? You're talking 110, 115 degrees. That's really, really hot summers. All right, so everybody's talking about this in Paris right now. What do you do? Is there some way we can slow this down or stop it or reverse it, whatever? One of the great dilemmas is developing countries like India and China. India is third in the world in greenhouse gas emissions. China's second, we're first, but okay. But these are developing, and actually we've taken really great steps to reduce our emissions, we really have. But these guys don't. They still burn anything that burns in order to drive their economy. And they're producing huge amounts of greenhouse gases. Do they have the right to do this, or should the Western world somehow subsidize them so they don't have to? I mean, that's one of the questions that they're talking about. Most people, and certainly most politicians, are not smart enough to try to understand the concept of global warming at all. And in fact, the entire thing has become totally political. A great fear of the unknown. How are you going to do this? How are you going to allow cultures to develop and become westernized, if you will, without poisoning out all the rest of the world. The name of this course is actually Chemistry and Society, and so this is like the first time we mentioned society. But these are things that we really need to think about. These are things that people really need to understand. This really is happening, and the solutions really are not simple. Mars. Apparently Mars once had oceans, probably had life, and it underwent a climate change. And now it is just this vast desert ball. All the water that's left is buried deep underground with minerals and stuff like that. If we allow the temperature of the Earth to go out of control, this is where we're heading, actually. So, again, these are serious things that we need to understand and be able to think about. Any questions? All right. Let me just do one thing here.